Alright, so today let's talk about the theory of a pericyclic reaction that is called the ring opening or the ring closing. Today's goal is going to be identify ring openings and closings and be able to predict the products based on the theory that we're going to go over in today's lecture. So the general way the reaction works looks like this. You have some sort of conjugated system, once again, and you react it in the presence of heat or light, and what you get is a closed ring form which has some conjugation. And this is in general reversible, so you could also have a closed ring like this, react it in heat or light, and get an open formed compound like that. The way that we demonstrate the mechanism when arrow pushing is simply the same, pretty similar to how we do the Diels-Alder. We just move this in here to indicate that we're making the new sigma bond that's going to be located here, and then we move the other two double bonds as well. So they're going to move along here, and again, this is how we represent it when we're doing the arrow pushing mechanism, but the actual true mechanism is a lot more complicated. It involves orbitals. So that's what we're going to be talking about today. How do the orbitals actually work when we're doing this mechanism? So right now I'm going to give you a very brief overview just so you have some context, and then we're going to slowly go back through it and justify exactly what we're doing. So suppose you have a conjugated system like this. Again, that just means you have your pi bonds oriented like this so that your electrons are delocalized throughout the entire pi system. And say the orbital that represents this system looks like this. Remember, when you have double bonds, those consist of p orbitals that are lined up like this. When you have a conjugated system, we could represent those as a molecular orbital, and say the molecular orbital that corresponds to the system looks like this. We'll explain how we got this diagram later on, but for now, just take it. Suppose that we change this conformation to this conformation. So we reorient the molecule, we do some bond rotations to allow this to happen. Okay, well, great so far. And then we say, okay, well, it has the exact same molecular orbital, so let's just draw that molecular orbital in this new conformation, and it's going to look like this. Okay, so far so good. So we had this, we had the molecular orbital corresponding to this. We changed the conformation, we kept the same molecular orbital. So the way that the electrocyclic ring closing works is that you have these orbitals on the end that'll move together, and they need to combine in phase, right? So both these shaded, lobes need to combine, or both these unshaded lobes need to combine. And once they combine, you'll have a new sigma bond that forms along here. Remember, for a sigma bond, the p orbitals need to be basically along the same internuclear axis, and for pi bond, they could be off the axis. But these will rotate inward, and they'll form the new sigma bond, and then these will readjust their electron distribution so that you get two double bonds over here. Okay? So that's generally what happens. So let's try to explain what is really how do we model this reaction? Right, so question one is, how do we get this molecular orbital here? Where does it come from? So how do we get the correct MO to do this pericyclic reaction? Well, remember that in our original molecule, which was this, we had 3 double bonds. So 3 double bonds is the same thing as saying that we have 3 pi bonds. And when you have a bond formed, you also have the existence of an antibond. So if we have 3 bonding molecular orbitals, which are these pi orbitals here, then we've also generated 3 antibonding molecular orbitals. So the way that the molecular orbitals work is that the one in lowest energy will be where the entire pi system is lined up. So this allows the electrons that are present in these orbitals to run all along the system. This is great. It has 0 nodes. A node is just when you have a jump between shaded and unshaded, as I'll demonstrate with the next one. So the second molecular orbital will have 1 node. So again, this went from shaded to unshaded. So now electrons that are present can only be delocalized here and here because they can't cross the node, right? Crossing the node is a big no-no. That's not something that could happen. So I'm telling you that we have 6 of these molecular orbitals that I'm drawing now. These are the lowest in energy. As you draw the rest of them, you simply need to increase the number of nodes that you have in the system. So these are the 6 molecular orbitals that could represent this system here. The highest in energy, we'll just have them alternating like this, so you get 5 nodes. Okay? So far so good. So again, more nodes means it's going to be higher in energy. As you can see here, the lowest has no nodes and the highest has 5 nodes. You might think to yourself, why is this true? And then you remember back to our fundamental, I guess, concepts from chemical bonding is that nodes mean less electron delocalization, right? As I was talking about here, if you have a node here, the electrons are trapped in this region or this region. They can't spread out as much as possible. What that means is when you have that lack of delocalization, you have more electron density in this region, because they can't spread out as efficiently. And when you have more electron density in an orbital, in general, you'll have a higher energy orbital. For the ring opening and the ring closing, the reaction will occur through the HOMO, which is again the highest occupied molecular orbital. If you have 3 double bonds, that means you have a setup that looks like this. Let me try to move this down. Okay, there we go. So again, as I was saying before, we have 3 bonding molecular orbitals. Those are going to be the lowest in energy. And we have 3 anti-bonding molecular orbitals. So those are going to be the 3 highest in energy, arranged by how many nodes they have. So since we have 6 electrons, we put 2 electrons in each of the lowest orbitals, and we get to here. So this is the highest occupied molecular orbital because it has electrons, and this is the lowest unoccupied molecular orbital because it doesn't have electrons, and it's the lowest in energy out of the 3 antibonding orbitals, again because it has the least nodes out of these 3 orbitals. So the reaction that takes place will take place through this orbital here, this HOMO, which is again, when we went back to the original overview, that's the exact orbital that I used here. So the orbital that you use for the ring opening or the ring closing is going to be the HOMO for the system. So you'll just need to be able to draw this molecular orbital diagram and be able to figure out what the HOMO looks like. And we'll look at some ways to even simplify that further to make your job super easy. So the next question comes with, okay, when I initially introduced this reaction, I said it could happen in heat or light. How does the presence of heat or light affect how the reaction is going to occur? So what role does heat or light play in the reaction? Well, it goes to how you draw this molecular orbital diagram. So what we've been looking at, the system we just looked at above, is the molecular orbital diagram that corresponds to heat. And I'm trying to fit everything here in the window. You have to forgive me if it doesn't exactly work out. All right, I think that fits everything. I'll move this over a little bit. Okay, so how does light or heat affect the reaction? Well, for heat, this is the molecular orbital diagram that we have. But for light, if you remember back to your radical reactions, how those radicals form is that you have the promotion of an electron from one orbital to the other. So, having a hard time putting this anywhere. I'll put it up here, I guess. Light promotes the movement of an electron. So here, if we're using light, one of these electrons will move up to the next energy level. So this is moved up to here. Now this is the HOMO, and this is the LUMO, because now this is occupied, at least half occupied, and this is still completely unoccupied. So if you're going to be doing the reaction in heat, you're going to be looking at this molecular orbital, and if you're doing the reaction in light, you're going to be looking at this molecular orbital. So it does matter if you're going to be doing the reaction in heat or light. What we have to figure out is, well, why does it matter so much? We'll come back to that briefly. So let's, I don't know, I have 3 O's there. Let's have another look at the reaction that we were doing earlier. and I'll sort of put a bunch of information out. So this is the exact same reaction we were looking at earlier, but I've indicated that these, again, this is the MO that we're using if we're reacting in heat, but pay attention to these orbitals here on the end, these p orbitals in this molecular orbital. Yeah, it's pretty confusing, but deal with it. So again, if we fold the molecule in this conformation here, these orbitals appear like this. I told you when the reaction happens, we're really interested in the sigma bond that forms here from these two p orbitals. So really, what I'm saying is, when you have the HOMO, really you only need to pay attention to how these two orbitals on the end are going to be oriented, these two p orbitals on the end. Because they're the ones that are important, they're the ones that are involved in the new bond formation. So, what I'm saying is, we only need to consider the p orbitals at the end of the HOMO. Okay? Let's look at an example that might demonstrate that. So, back in this over here, on the left, oh god, we have heat, and on the right we have light. So this is the HOMO if we're doing the reaction in heat, and this is the HOMO if we're doing the reaction in light. So over here, just notice that we have these two as our ending orbitals, and these two as our ending p orbitals. So on the heat one, both are shaded on the top, and in the light one, we have a shaded on the top and a shaded on the bottom. So if we look at our system for heat and light, it'll look like this. Again, both shaded, and then shaded, and shaded like that. Okay, so when we do the ring closing like this, if you're, I guess, paying attention, you'll notice that the way that these orbitals need to rotate to align is going to be different. In this case, this is going to move in clockwise, and this is going to be moving counterclockwise, whereas in this case, this will be moving clockwise, and this will be moving clockwise. So the way we describe this is that when they're rotating in the opposite direction, it's a disrotary motion, and if they're rotating in the same direction, i.e. both clockwise or both counterclockwise, we call that conrotary, okay? So now the new question is, why do we actually care whether the ring closing is going to be conrotary or disrotary? Well, let's go back to that reaction one more time and change the molecule slightly. Say now, instead of the previous molecule where we just had hydrogens attached here, say we have a chlorine and a bromine just hanging out on our molecule like this. Well, let's go back to the previous example. For heat, we're going to have shaded, shaded, and for light, we're going to have shaded, unshaded, okay? And like I was saying before, the way that you close the ring through the interaction of those two orbitals is going to be in a different motion. This will be in what we call the disrotary motion, where we have a clockwise and a counterclockwise, and this will be conrotary, where it's clockwise and clockwise. So as you rotate those orbitals, what you'll see is that when you're lining these up, the chlorine and bromine will be located in different places depending on whether the motion is disrotary or conrotary. Here, as this moves clockwise, the chlorine moves from what is supposed to be the 9 o'clock position to the 12 o'clock position, and here this is moving from the 3 o'clock position up to the 12 o'clock position. And over here, you have something at the 9 o'clock position moving to the 12, and over here, you have something at the 3 moving to the 6. Okay, well again, why does this matter? Well, the mechanism, when we draw the arrow pushing mechanism, will pretty much look the same, right? We're just going to be moving these around like this in a circle, much like we do with the Diels-Alder, but depending on whether we're doing it in heat or light, we're going to have different p orbitals out there on the front here. So at these ends of the molecules. What that will result in is, in the final conformation, these groups will be different. So you actually get two separate molecules here. So if you're looking for a product that has both of these on a wedge, or one on a wedge, one on a dash, you need to be careful about whether you're going to use heat or light to close the ring. Okay, so there is one more thing we should talk about that's going to simplify your life greatly. How can we determine if the ring closing will be conrotary or disrotary, right? So in this case, when we use heat, the ring closing was disrotary, and when we use light, the ring closing was conrotary. But what I'm telling you is this is not necessarily always going to be the same pairing. We could have heat and a conrotary closing. We could have light with a disrotary closing. So we need to figure out a system for how to tell, based on whether they're using heat or light, if the ring closing is going to be conrotary or disrotary. So it again goes back to paying attention to those molecular orbitals that we had. But again, I want you to ignore all the p orbitals except for the ones that are going to be on the ends. So we have this here, but what you really should be looking at is just the ends. So these are on the same side, now these are on the opposite side, now these are on the same side, now these are on the opposite side, now these are on the same side, now these are on the opposite side. You should see a pattern emerging here. So when they're on the same side, that's what we're going to call symmetric, right? Because if you took this and you just folded it over like this, they would line up, and if you took this and you folded it over, it would not line up. So this is symmetric and this is anti-symmetric, and they're always going to be alternating like that. So when we're looking at actually trying to close the ring, this will be symmetric and this will be anti-symmetric. Cool so far? I hope so. So as you'll notice, when it's symmetric, right, it's going to be the same as if we had this going on. So now we have a different way of looking at it. When it's symmetric, you're going to be having this disrotary motion going on, and when it's anti-symmetric, you're going to be having this motion going on. So symmetric will in general correspond to a disrotary motion, and anti-symmetric will in general correspond to a conrotary motion. Okay? So you're probably a little confused at this point, and that's okay, because there's a lot going on here, but let's put it all together. So let's predict the product of a different reaction and apply our rules to that system. So say we have this molecule, and this time we're going to be reacting in heat, and we have the same molecule, and this time we're going to be reacting it in light. So the first step in solving this problem is determine what the molecular orbital diagram looks like for this system. So you know that there are two double bonds, which means that you're going to have two bonding MOs, and whenever you have a bonding MO, you generate the existence of an anti-bonding MO. So without looking at the whole complicated mess of p orbitals, we just know that our diagram is going to look like this, with our two bonding MOs down here and our two anti-bonding MOs being over here, higher in energy. We know that we have 4 electrons, so we fill it up like this. And we can tell that if we have light, we have the promotion of 1 electron from this level up to the next level. Hopefully you follow along so far. The second thing we do is we determine the HOMO for each of the systems. So for heat, that'll be here, because this is the highest occupied molecular orbital, and over here, now this is the highest occupied molecular orbital. Okay, so now once we've done that, the next step is to determine if that HOMO is symmetric or anti-symmetric. That's also not so bad, because remember, it's always going to start with the lowest one being symmetric, and then it's simply going to alternate. So this will be anti-symmetric, this will be symmetric, this will be anti-symmetric. So now we know we have an asymmetric HOMO for heat, and for light we're going to have a symmetric HOMO. Okay? So now we have a lot of information, and now we can work with that information. So now the next step is to determine whether or not it's going to be conrotary and disrotary. So in this case, heat was anti-symmetric and light was symmetric. And again, that comes from over here. The HOMO is anti-symmetric, so this is going to be shaded, and this is going to be unshaded up here. And this we said was symmetric, so this will be shaded, and this will be shaded as well. And we know that when we have an asymmetric, we're going to have clockwise and clockwise, so that'll be conrotary. And over here, when we have symmetric, To close the ring, you're going to need a disc rotary motion, so this will be moving clockwise and this will be moving counterclockwise. So the next thing you do is you rotate it so that it works out. So when this rotates, since this is moving, this is inward, this is going to be moving from the 3 o'clock to the 6 o'clock, and this over here, since it's looking inward, it's at the 9 o'clock position. If you're going to be looking at it dead on, and by dead on I mean like you're pretty much looking at it so it's straight out in front of you. This is going to be, again, at the 9 o'clock. As it's rotating around, it's going to move to the 12 o'clock position. Over here, this is at the 3 o'clock. It's going to move down to the 6 o'clock again. Over here, since this is at, well, the orbital is oriented to the 12, this is oriented to the 9, so this is going to move from the 9 to the 6. So in your final product, what you're going to expect is that this is going to be down, up, right? Because this methyl is down, that methyl's up. And over here, this is going to be down, down. So now that you know that, all you need to do is first draw what your mechanism is going to be. So draw your mechanism. So this will move like this will move like this. You're going to get the 4-membered ring. And for heat, it'll look like this, because remember, down, up, and over here, for light, it's going to be down, down. Alright, that's pretty much everything you need to know about the electrocyclic ring closing. So in the next video, we're going to be doing a bunch of practice problems. If this last step over here, if this confused you, getting these oriented correctly, that's pretty much going to be the focus of the video. But there's a pretty neat trick that you use to figure out how it's going to be oriented, so we'll be talking about that. So if you're confused, watch the next video. And slight footnote, technically this won't happen. So a 4-membered ring closed thermally is not favored at all by sterics. So this is the one exception you need to know from this reaction type. It might show up on your final, so make sure to pay attention.